Hello, everyone. My name is Astrid Modera, and I'm a PhD student working in philosophy of biology here in Namur, Belgium. The topic of my presentation is, as you can see it, a relational definition of life for astrobiology. Of course, my presentation will be short, but as clear as possible, and I hope will bring enough interesting material to create a vivid discussion during the session. The aim of my presentation is to propose a usable definition of life for astrobiology. The question of the definition of life is one of the most important yet difficult conceptual issues for astrobiology. It's crucial because without a proper definition of life, we won't be able to actually do astrobiology. If we wonder if there is some kind of life outside the Earth, we need to define as clearly as possible what life is. If we want to be able to recognize living entities, we have to know what living entities are. So we need a useful and usable definition for something we don't know yet, we are not even sure exists, and might be very different from everything we know, and there's still a lot of things we don't know about life on Earth. The definition currently used by biological scientists are composed by two approaches of living entities, approaches often combined. The first one is the approach based on what living entities are, and the second one on what they do or what they are capable of. The first one might be called reductionist approach and is based on physical chemical composition of living systems. For example, living entities are systems made out of CHNOPS for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The second one might be called a Darwinian approach and is based on the ability of living systems to show signs of Darwinian evolution or adaptation. The difficulties with those approaches are that for the first one, it's not enough. A lot of non-living entities are also made out of CHNOPS, and that it can narrow too tightly the possible large diversity of bricks for life in contexts very different from the Earth. For the second one, the difficulty lies in the timing. We don't usually have time in astrobiology to wait for generations of possible living entities to determine whether or not it shows signs of Darwinian evolution. And moreover, it lets outside of the living realm some peculiar terrestrial organisms that don't reproduce with enough variability or don't reproduce at all, like sterile organisms, for example. We need something else. The approach I'll present to you today is the one developed in relational biology. It's a branch of biology created by two physicists/biologists of the 20th century, Nicolas Rashevsky and his student Robert Rosen. Relational biology is a holistic approach of the organisms. We are considering them as wholes and not focusing uniquely on their parts. This approach is mathematically developed and described. which provides a very different and interesting point of view on life. The central idea in relational biology is the focus on relations inside living systems. The claim is that what is unique in organisms or living systems is the relations between this system's components, it is between the functions. The leitmotif of relational biology is throw away the matter and keep the underlying organization, meaning that what matters in living entities isn't the matter, CHNOPS, for example, but the interactions creating the system, organizing it. It allows us to take distance from the reductionist/biochemical approach of life. Rosen developed in 1958 a model, a theoretical, mathematical representation of living systems called MR system. The idea is that a living system contains three main functions: metabolism, repair, and replication, the M and R in the name MR system. Those functions might be represented in a model showing three processes, and those three processes cause each other in an efficient way. Here, the metabolism, FAB, is caused by repair, PBF, itself caused by replication, BFP, itself caused by the metabolism. A quick word about those functions. They were found by Rosen by looking at a cell, but the replication function isn't the one happening inside the nucleus during mitosis. Rosen chose this word in 1958, as I said, when molecular biology was at its beginnings. Its late developments will show that replication doesn't act like Rosen supposed it does, but the word was kept. The idea is that that model, the MR system, is a correct model of living entities. We just have to compare the potential living form to this model, and if it fits, it means that this system is alive. To formalize those relations between functions and this whole model, Rosen will use a mathematical tool, the theory of categories. That theory, created by Eilenberg and McLane in 1945, contains concepts that can rigorously represent very abstract organization. Two of these concepts are functors and natural transformations. The exact action of a functor is to create relations between relations by creating a link between the objects and another link between the arrows connecting those objects. Here, the functor is the three orange arrows. It's a great tool to work at a very abstract level. But this is one of the reasons why relational biology is marginalized. It's too mathematical and too abstract for a lot of contemporary biologists. A definition of the organisms can be read in the MR system. An organism is a material system closed to efficient causation. Here is another representation made by A.H. Louie, Rosen's student, of that model, showing exclusively the efficient causations and their closure. The term of efficient causation is as you've already noticed, a direct reference to Aristotle and its theory of causation. Rosen, to represent functions and processes by using the theory of categories, noticed that a process can be explained in an Aristotelian way with every one of the four types of causation. He suggested that what assures the autonomy of the organism is that closure. Every function, every process is caused inside the system. Living entities are still open systems in a thermodynamical sense. There are constant flows of matter and energy between the inside and the outside of the organism, the environment. But every process is explained within the system. It contains its efficient cause. This approach of living entities, this definition of life, can have several advantages for astrobiology. First one, it avoids to wait for signs of evolution or adaptation. It's still a diachronic definition, by opposition of the small error in the abstract of my presentation, where I wrote that it's a synchronic definition. No, it's about processes and functions, so it takes time, but at a very shorter time scale than evolution and adaptation. But yes, we're still focusing on what organisms do. It's diachronic. The definition doesn't depend on specific materials. So we can imagine very different breaks for living systems. For example, we can imagine life without carbon. If the system can express the three functions of an MR system, and if they are closed to efficient causation, that's it, it's alive. And third, using the theory of categories can help us focus on organisms as wholes and create theories at the biological level without being dependent of chemistry and physics. It can really be useful in the case we are actually in front of potential living entity. It's a definition that can be used in the context and in practice, but it's a very specific tool. It doesn't meet all the demands of astrobiology because it won't help us to distinguish between potential livable planets or to show us where to look for such walls. To conclude, I'd say that despite some practical difficulties I didn't really confront here, the relational definition of life proposes a refreshing point of view on life, and it can allow biologists to defend their discipline and show its peculiarities. We don't have to question life from physics or chemistry to have a practical picture of it. I would like to thank you all for listening to this presentation, and I can't wait to discuss it with all of you. Thank you.